Hello, college algebra. Today we are going to continue talking about exponential functions, but now we are going to be talking about that within the spirit of money and specifically compounding interest formulas. And so this is real life applications. This is how a lot of money grows in accounts. And so this looks like a scary formula, but it is simply another exponential formula. It's just got a little bit more involvement. Recall with our exponential formula, it was y equals c times a to the x. C was that initial value. In this instance, p is the initial value. That's the principal. It's like if I were to spend, or if I were to initially put in $2,000 into an account, that is our starting point, what you initially put in. When you talk about it with money, they call it the principal. And then it's going to do all of this math. It's going to have a certain rate. Different accounts have different rates, how much it compounds a year, and over a certain amount of time that will all give you an output, which is normally Y, but in this case it's notated with an A because it's the amount left in the account. Again, these are just variables. So P is that initial amount. R is going to be your interest rate. Very importantly, you always need to represent this value as a decimal. Remember, we talked about decimals in the last video, in the end of the last video. I'm not going to go over how to convert decimals again. So if you need that or need supplemental information, please reach out. N is the number of times it compounds a year. That basically means how many times am I taking the new money and adding more of the rate to it. And sometimes that happens quarterly, sometimes it happens monthly, daily. That amount is just continuing to grow and grow and grow. And then T is time in years. So for example, if I was compounding monthly for 1 year, this would be 12 times 1. And maybe I have a certain amount after that. Or if I was compounding monthly after 2 years, that'd be 12 times 2, 24. That would be the amount. So historically, if you leave money in an account longer, it should grow. Hopefully you have a growth and your money is growing. So let's kind of see what this looks like as a word problem. So it says, suppose $2,000 is, let's zoom in a little bit. There we go. Suppose $2,000 is deposited by a 20-year-old worker in an individual retirement account, IRA, that pays an annual interest rate of 4%. I'm just going to go ahead and turn that into a decimal. How much money would be in the account after 45 years if the interest was compounded annually? Okay, so we need a few things when we are, putting in this information. We want to know how much money would be in the account. So we want to know if we put all this stuff in, what is A? So that's what we're figuring out. Look at the variables. We need P, we need N, R, and T. Okay, I'm going to go ahead and just write that down here. I need P, I need R, I need N, I need T. Okay, P is principal. P is that initial amount. That is what you started with. I started with $2,000. Whoops, that is the example I used earlier too. Sorry. It's not always going to be $2,000. Don't worry. Let's see. R is the rate. We already identified that. The most important thing with rate is to convert it from a percentage, which it will almost always be given to you, to a decimal. T is how many years. So let's see. How much would be in the account after 45 years? N is probably the trickiest thing to identify. It says, and N is how much time it is compounded. So with this one, it says it is compounded annually. That means it is only compounded once a year. Versus something like quarterly would be 4 times a year. So you're saying, how many times does this happen a year? So quarterly is 4. Monthly, there's 12 months in a year, would be 12. We have something down here that we're going to have like as a little cheat sheet. And ideally, it's going to compound a lot. Like you want it to compound a lot because that means it's taking that new amount and it's adding more money to it. And it's going to continue to grow. So now what I'm going to do is I'm just going to put this in the formula. I'm going to try to show these at the same time. So A is equal to 2,000 times 1 plus R over N, 0.04 over 1 times N, which is 1, times 45. So these are both as an exponent. I'm going to go ahead and show you how I'm going to put this in my calculator. I'll do this one time. It'll always be the same. So even though this is 1, I'm still going to write the 1 because it's not, the N's not always going to be 1. So I'm going to put 2,000 times 1 plus. I have this little fraction button in my calculator, alpha x, and it puts it, as a decimal. As a fraction. If you don't have this, then I would just put that fraction in parentheses. Sorry, that is hard to see. But you want to make sure that that fraction kind of stays together. Sorry, let me do this. Then we're going to do exponent, the caret. And the 1 times 45, both of those values are as an exponent. And so what this tells me is that if I let that $2,000 sit after 45 years, it's going to be at a value of basically $11,682. I'm going to go to 2 cents though when I talk about money, because that is how we represent money, right? Our cents value only go to 2. Now, same question, how much would be in the account after 45 years if the interest was compounded quarterly? The only thing that's changing here, according to this question, is that the interest is being compounded quarterly. Quarterly means 4. There's 4 quarters, right? In a dollar, there's 4 quarters in a year. So that 1 is changing to 4. I'm going to go ahead and put that back in my calculator. And what I just did was I scrolled up, I highlighted my previous answer, and I can edit it. So I'm just going to change that 1 to 4, or you can do it all over again. It's whatever you want to do. And I get a new value, which is $11,991.60. So $11,991.60. In this scenario, which one is better? Well, in my view, better would be the one that gave me more money. So quarterly seems to be the better answer here because you made more money. I have this written out better in my notes, but you made more money when it was quarterly. It's because it was compounded more often. It takes that new amount of money, which grows from 2,000, so it's no longer 2,000. It's like maybe over a certain amount of years, it's more than this, which continues to compound and grow and grow and grow and grow. Again, it's not linear. It's exponential. It's growing up, 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 up. And so also the amount that you put in as the principal is nice too. That initial amount is really helpful. It'll help it get a good start. So if you're thinking about investing, a good initial amount is helpful too. But something's better than nothing. So if you decide to invest, even if it's a small amount, it's not a bad idea. Okay, so this next example, I will go ahead and read. So it says, suppose a student took out a $5,000 loan that had an interest rate of 7.05. I'm going to go ahead and change that. 0.0705. Move that decimal place 2 places to the left. How much money would the student owe after 2 years if the interest rate is compounded annually? semi-annually. I'm sorry. Think of like a semicircle. That's half a circle. Semi-annually, your n would equal 2. Now, I recommend that you pause the video and try to identify some of the other variables that you need for this formula. I'm going to go ahead and go. So please pause it if you would like to try this on your own. All right. My P is 5,000. That's the initial amount that I took out. My interest rate is 0.0705. My N is 2, and it wants to know how much I owe after 2 years. So I'm going to put that in to my formula, and yes, this doesn't always necessarily have to go with investments. It could still just sit in an account and say how much you owe after a certain time. And it is also true, the longer you let student loans sit in an account, the more you're going to have to owe. All right. Sorry. Okay, so I do 5,000 times 1 plus the rate divided by n times the n times year. Again, I'm going to put this in my calculator just like I did earlier, and I will get about $5,743.16. So now I owe $700 more than I was loaned. So again, just be really careful about loans. Okay, let's do another one. How much if it's compounded monthly? Again, I recommend that you pause the video and try this on your own. Let's see if this is gonna... There it goes. Monthly, there's 12 months in a year. So in here would be 12. Everything else is going to be the same. Still 2 years. It's basically just presenting a different scenario to you to see how, if you're given the same rate and all of those things, but it's compounded differently, how that can really impact the ending amount. So the only thing I'm changing here is the end from 2 to 12. And when we do that, we get $5,754.75. Yeah, it's a little more, not a lot more, but I would still rather it be compounded semi-annually because I would owe less money. So when it comes to you, sorry, I'm trying to get this to focus. There it goes. When it comes to you owing money, you'd rather it be less than. But when it comes, of course, to you making money, you'd rather it be more than. And yes, it's not a huge difference. It's like, I don't know, $11, but if you are looking at this over a time period greater than 2 years, it could really add up. Okay. So really quick, here's like a little cheat sheet for you, I guess, if you want to call it that. Annually, this is what N would be. If it uses the word annually, N is 1. Semi-annually, N is 2. Quarterly, N is 4. Monthly, N is 12. Weekly, how many weeks are in a year? That's kind of what I asked myself. 52 weeks in a year. Daily, there's 365 days in a year is what we use. Even you don't have to assume it's a leap year. Continuously, we don't know that one yet. Okay, so if it uses any of these values, I'm sorry it keeps, let's do this. Sorry, it keeps blurring. There it goes. So we know all these. If these words are used, these are our N's. But if it says compounded semi-annually, again, the N is 2. Compounded daily, this is your N value. There are some instances where it says is compounded continuously. So what exactly does that mean? Well, let's find out. Okay. A lot of what we've been talking about thus far has been talking about exponential functions. Exponential functions can be used to model functions and to figure out how much money you might make at a certain point if it's compounded at every month or every year, or whatever that might be. But when it's compounded continuously, it means it continues to grow, like literally continuously, like nonstop. It just takes that amount of money that's in there and does all the math, and then it takes the new amount and just keeps on kind of doing this formula like nonstop. So it continues to grow, 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 grow. So it's, again, letting that done more frequently and becomes larger without bound. What we use to represent that continuous growth, we will use the natural exponential function. That natural exponential function is f of x equals e to the x. E just represents an irrational number. And it was this mathematician, we call him Euler, he came up with this. And this number shows us basically and models exponential continuous compound growth. So this looks a lot like the other formula. You still have P. Now you just have E to the RT. E is a value in your calculator. E is not a variable. The variables that you have to find are P, R, and T. Okay, so let's look at what this might look like with the function that, like what we were just doing. A principal in an IRA is $2,000. That is what we started with. The interest rate is 4%. I'm going to go ahead and turn that to a decimal. Compounded continuously. That is how you know you are going to use this equation versus the other one. If it said compounded monthly, you use this one. Compounded annually, you use this one. Anything other than compounded continuously, you use the other one. When you see compounded continuously, you use this one. How much money would be in the account after 45 years? T is always the year value that we are given. So I'm going to put this in my calculator, but I'm going to write it out really quick. A is equal to P is 2,000 times E to the R times T. All right. Here we go. A is equal to 2,000 times. E is in your calculator. If you look at the ln, it's right near log. Ln is below log, or it should be. Above ln is e to the x. So you're going to have to press second, e to the x. You'll notice it just puts e in there for you, and it automatically makes you put an exponent. E has relationships with exponents that we will talk about soon. So now I'm just going to put in that 0.04 times 45 and get my output. I get an output of $12,099.29. That is how much would be in the account after 45 years. Okay. Let's keep on keeping on. So it says the population of Arizona was 6.6 million in 2010, and it was growing continuously at a rate of 1.44%. I'm going to go ahead and change that. Assuming the trend continues, estimate the population in 2016. Okay, it's not actually telling us the years. So from 2010 to 2016, 6 years. That is 6 years. That is how I'm getting the T. It didn't just explicitly tell me. You can even do 2016 minus 2010 in your calculator and you'll get 6. Then what did we start with? We started with 6.6 million people. So I'm going to do exactly what I did earlier. I'm going to put this in my formula. If you want to pause the video and see if you can do it on your own, please feel free to do so. Okay. I'm going to go ahead and put that in my calculator. 6.6 second ln. That'll get me my E. 0.0144 times 6. This value gives me the value in millions. I'm just going to go to one decimal place. So 7.2 million people, we can approximate, will be living in Arizona in 2016, which I guess we could check this model because that year is already passed. All right. If you want to try number 3, go for it. You're more than welcome to do so. I'm going to go ahead and go, so pause the video if you want to do this on your own. Sometimes after a patient takes a drug, the amount of medication in the bloodstream can be modeled by our continuous compound formula, where P is an initial concentration in milligrams per liter, R is the hourly percentage decrease in decimals of the drug in bloodstream, and T is the elapsed time in hours. So it's telling us that T is different than years. That's important. And that can happen as long as you kind of make sure that it's defined in the equation or in the word problem. Suppose that the amount of medication in the bloodstream is initially 2 milligrams per liter. Okay, that initial amount, again, telling us is our P. And that R is negative 0.2. This is already in decimal form. It's telling us. So the rate they have already done for you. You don't have to change it at all. Write a function that finds the amount of medication in the bloodstream. All we're doing is writing the function. It's like putting things in terms of in terms of X and Y. All we're doing is putting our principal, our rate, and our T. That's all you're doing. And now you have a function that you can figure out after so many hours how much medication is still in the bloodstream for 1 hour, 2 hours, 10 hours, which is what we're about to do. So find the amount of medication in the bloodstream after 3.5 hours. So now we're actually going to put in a T. A is equal to 2 times E to the negative 0.2 times T, which is 3.5. I will go ahead and do that. 2 to the E, negative 0.2 times 3.5. I get 0.0. I'm just going to go to 2 decimal places, 0.99 milligrams per liter. When does the amount of medication in the bloodstream, well, hang on, let me pause. A few things. So again, it could have asked us many different questions. After 3.5 hours, after 5 hours, after 10 hours, we have that function so we can put in a time and get an output. I know I've been going to 2 decimal places on a test. I will be specific. I know the homework sometimes is not, so please just let me know if you have any issues with that or seek any clarification. I can always reach out to Cengage. Next, that's great. We can find out for any T what the amount is. But what if it asks differently? When does the amount of medication in the bloodstream reach 1.5 milligrams per liter? This is asking things differently. It's wanting to know, how long does it take? What is the T to give me an output of 1.5? So it's giving me the A. It's saying when A is equal to 1.5, how can I find how much time that represents? How much time would give me an output of 1.5? We know that 3.5 gave us an output of 0.99, but what T gives us an output of 0.99? I'm sorry, of 1.5. So the big question here is, how do we solve for t, basically? How do we solve for t? But it's an exponent. Usually when we solve for x, or a variable, we have a lot of tools in our tool belt. If it's being multiplied by 2, we can divide by 2. If it's being square rooted, we can do the opposite. Like, we have all these things that we can do the opposite for to try to solve a variable. But what if that variable is an exponent? How do we solve for t when it's an exponent? I'm going to put a explanation point because we feel very strongly about this. So basically, we are going to have to do a little bit with logarithmic functions. And you'll notice that in your calculator, ln and e to the x are together. That is by no coincidence. ln and e to the x have a relationship. All right, so let's dig into logarithmic functions. So the long story short is, we're not answering this yet. This is a little introduction to logarithmic functions, but we can come back and answer it. All good. Okay, here we go. Logarithmic functions. Okay, there we go. The inverse of exponential functions are logarithmic functions. Do we remember what inverse is? Inverse just means that x and y's switch. So this is really important. When the unknown of a variable of an exponential function is in the exponent, you basically just have to use logarithms to solve it. So, for example, this one. If x is in the exponent and I wanted to know what x gives me an output of 300, I don't have a solution to that. Like, I don't know how to get this exponent. How do I even do that, right? Well, the solution is basically our math tool belt says that logarithmic functions and exponential functions have a relationship, and that relationship is I can manipulate the way this looks, change the way it looks to make it in a way that I can solve this. Okay, really quick, let me just give you an example. What I mean by, let's see, y equals, let's do 2 to the x. What do I mean by inverses? So let's just give an example of 2 to the x. And again, this is from one of the first homework videos that we did, but you can put these values into your exponent. 2 to the negative 1 is 1/2. 2 to the 0 is 1. 2 to the 1 is 2. So I have this value. You don't know this yet, but I'm just telling you. Take my word for it. The logarithmic function that goes with this exponential function is log base 2 of x. That 2 is little for a reason. And it is no coincidence that 2 is both in the exponential and the logarithmic function. And I don't really know anything about this logarithmic function, except that I just told you they're inverses. And if they are inverses, that means that the values can be switched, right? The x and y values are switched. That's how inverse functions work. Inverse functions are not going away. So if you did not understand that unit, please go back and look at the videos. Please ask help, seek clarification, all the things. Okay, so just so you know, that's kind of the relationship between the two of them. And we're going to keep working through this, but I just wanted to do a quick little recap about what that means in terms of what we've known about inverses and what it will mean with exponential and logarithmic functions. So what does a logarithmic function look like? Well, I just showed you a little bit. It's f of x equals log base a to the x. Again, this is your x and y, and the base will vary. It's like anything else, like with exponential functions, it could have been 2 to the x, 3 to the x, all the things. We have things called common logs. A common log is a base 10. It's kind of like a square root. We don't put a square root, technically has a 2 here, but we don't put it because it's so common. Same thing with common logs. If you just see log without a number, you just assume it's base 10. And natural log is just log base e. So if you go to your calculator and you press log, well, it would help that this is on. If you press log, this assumes log base 10. And if you press ln, ln is the same thing as log base e. Again, we'll talk a little bit more about that. All right. So let's do some graphs and just kind of start getting an idea of what these functions look like. Okay, so if you want to, let's do math. All right. Okay, I'm just going to tell you, because we don't have too much in our math tool belt yet to try to figure out what this looks like in our as a graph. Because here's the thing. When I say, okay, let's graph this, and I go to y equals, and I go to log, there's only a few log options. There's log and ln, which is fine, but those are base 10 or base e, and this example gives me log base 3, so I'm a little stuck. That's okay. We will eventually get to how you can actually graph these. What I'm going to tell you right now is most logarithmic functions are, again, the inverse of exponential functions. But instead of going like this, like an exponential function, they kind of go a different way. So you're going to see some similarities, but you're definitely going to see some differences. So what this tells me is the initial logarithmic function, where it was originally, is moving 2 places to the left. Anytime something's directly associated with x, 2 places left. Anything that time this is directly associated with x, it goes the opposite. So you would probably think that means right, or that means increase. You're actually going 3 to the left. And that's okay. I can kind of show you how we get there too. In order to find the domain of a logarithm, you're basically going to put whatever that parentheses is equal to 0 and solve. That's going to tell you what x is going to get really, really, really close to but not be able to touch. That is called an asymptote, and we'll get there. Also, I know I keep saying that. We're really just scratching the surface here. So I'm going to make that little dotted line where x is equal to -2 to kind of indicate to me that I'm going to get really close to it but not touch it. And I'm just going to give you some values in this graph. The point -10 exists on this graph, and the 0.11 exists on this graph. And it's going to look something like this. Again, you don't know how to construct this yet, I'm assuming. And if you're like, where are you getting this? Don't worry, we will get there. I'm just kind of starting to show you what this looks like. So I can also kind of get an idea of the domain. The domain can get, again, left to right, get really, really close to -2, but it's not going to touch it. So I'm going to put a parentheses, not a bracket. So basically start at -2, get really close to it but not touch it, and then I keep going forever and ever and ever and ever and ever. A lot of logarithmic functions mimic this. So let's try this. Let's just talk about the domain for a second. I actually want to skip number 2 for now because I don't want to confuse you, and I want to get into graphs in a little bit. But if we kind of stick to that, I can put whatever is in my parentheses and set it equal to 0. And this tells me what x cannot equal. Again, if this moved it 2 places to the left and it was positive, kind of opposite again, this moved the graph 4 places to the right. So if a logarithmic function originally looks This is a very rough sketch. Something like this. I'm moving it 4 places to the right. Doot, 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 doot. And now it's going to look something like this. This is a very bad graph. But it's going to mimic this in that this was at -2 and went to infinity because that started where x couldn't touch. Same thing here. If I wanted to try to find my domain, I would say it starts at 4, it doesn't touch it because there's an asymptote here, and it goes to infinity. If you want to try this next one, feel free to pause the video. But I'm going to go ahead and solve for x. I'm going to set it equal to 0 and solve for x. That value tells me what x cannot be, and that x is going to start at -1/3 but not touch it. There's an asymptote there. It's going to get really close to it, but it can't touch it, and it's going to go on to infinity. It's not always going to be like this. There will be situations where it could change a little bit, and we're going to figure out how to graph these with a little more accuracy. But for now, all you need to know is that an asymptote exists, and so that's why we can't touch the value. We can just get really close to it. And the other thing that you need to know is, really the main thing, is that logarithms and exponential graphs equations are inverses of each other. So we can get really, really close to values, but we can't touch it. And at this point, you should be able to do the next homework, and we will get into a little bit more and the relationship that exists between logarithms and exponential functions in the next video. We are barely scratching the surface here. I know a lot of the things I've said today too when we've gotten to logarithms is we'll get there, and we will. We really will. Again, we're just kind of doing a very brief introduction to logarithms today.